this video, we're going to take a look at the magnetic field due to a current. And this is different than the permanent magnetic field. This is one that we can fine-tune, which is really helpful. Up until this point, we have been working with magnetic fields, figuring out what they do, but now we should also look at where they come from, and that's what this is about. If I have a wire that carries a current, that wire will produce around itself magnetic fields, and those magnetic fields will make circles around the wire. We have done one version of a right-hand rule that was about finding forces. I want to do a different version of a right-hand rule for this. So this right-hand rule is going to work something like this. I'm going to try and draw this out. Got some funny nail shapes going on. So if I've got a right-hand rule that looks something like this, I would like to put my thumb in the direction of the current, and then my fingers will curl in the direction of the magnetic field produced. It's convenient because nothing changes assignment from previously. Everything is still exactly what it was. So let's see what I can do with this. In this case, I would take this wire that has a current going to the right. I'm going to grab the wire with my right hand and point my thumb in the direction of the current. And when I do that, my fingers curl around like this. Which means my magnetic field has to come in front of this, and then behind it's going to go upward. If I want to look at this from the side, that means it's going to look like this. I will have a current coming at me, and then I'm going to produce magnetic fields around this current that will point in this direction. Now this thing is a long straight wire, and there are a couple of assumptions being made here. The big one is this. This wire goes on forever in both directions. Now that is obviously not something that's going to happen in real life. But consider this. If I've got a wall that is this long, and I stand right here, really close to it, the angle that I would look at, it would look very much like this wall goes on forever. If it did go on forever, I would look at an angle of 0 degrees here. Instead, I'm looking at an angle of maybe 1/4 of a degree or something like that. So very near a wire, this wire will look like it goes on forever in both directions. It's a good approximation for that. For this long straight wire, I'm going to get a magnetic field that looks like this. B equals mu naught I over 2 pi r. R is the distance that I am from this wire. So if I've got my wire like this and I'm looking at this location right here, R is going to be whatever that distance is. This mu naught is called the magnetic permeability of free space. And it has a value that's pretty easy to pick out. Mu naught is going to be 4 pi times 10 to the negative 7th, and that is Tesla meters per amp. There is a different value that you've already worked with, and that was the permittivity of free space, epsilon naught. And it turns out that if we take that epsilon naught and mu naught, multiply them together, and go 1 over the square root of that, we get c, which is the speed of light. In a vacuum. So that's an interesting thing. We've got this long straight wire, and that's one of the geometries that we are able to work with. In this course, without calculus, we are able to work with exactly 3 geometries. So that was one. The others are not going to be too bad. What if I have a wall that's fairly long, and I stand near the end of it? Well, in the one direction, I'm straight up. In the other direction, this goes on forever. This is called a semi-infinite wire. This is a wire that goes on forever in one direction and not in the other. So what that would look like most of the time is I've got a wire like this. It's carrying a current. I'm looking at this location right here, but this wire is shielded in one direction and not in the other. So over here there's some kind of a shielding that stops it, that stops the magnetic field. When that's the case, I have a wire that goes on forever in one direction and doesn't go on at all in the other. Here's the distance from that wire, r, and my semi-infinite wire, I'm going to get B equals half of mu naught I over 2 pi r. Not too bad. I've got one more, and it's this. I'm going to do this as 2 pieces. If I've got a current that goes around in a circle, I'm able to find the magnetic field at the center of this thing. Now, if I grab onto this wire with my right hand, with my thumb pointing upward this way, I'm going to get magnetic fields that point this way. In front of my wire, I will get a magnetic field that goes left to right. Behind the wire, I get a magnetic field that points right to left, which means inside this circle, I get magnetic fields that point into the screen. Outside the circle, I get magnetic fields that come out of the screen. These add up differently, but if I can look at specifically the center of the circle, then over here I'm going to get this magnetic field. From this little portion up here, I'm going to get a magnetic field. And so at the center, all those are going to add up, and the center is the same distance away from each of those little pieces of current. So the B field at the center is going to be mu naught I over 2r. Now you might look at that and say, wait a second, hold on. The one that's straight has a pi in the formula, and the one that's curved doesn't have a pi. That doesn't quite feel right. And you're right, it almost doesn't. But remember, mu naught has pi in it, right? It's a 4 pi times 10 to the minus 7th. So over here, I'm really getting a 4 pi times 10 to the minus 7th times my current over 2r. I guess if I used a capital R here, I should use a capital R here. So there is a pi in here. Back here, this has a 4 pi in it. And this pi will cancel with that pi, so the pi's cancel because there's a pi in the denominator. So for a full circle, I get mu naught I over 2r. There's just a little bit more. I don't have to do a full circle. Maybe instead of a full circle, most of this thing is shielded, but right here, this region is unshielded. And maybe this region subtends an angle of theta. Now, if that angle is 360, I get the full circle. If the angle is less than 360, I get less than the full circle. So I'm going to multiply this by theta over 360 degrees if I'm working in degrees, or theta over 2 pi, I guess, if I'm working in radians. Now I've got the magnetic field due to not just a full circle, but any arc. That's it. Those are my magnetic fields due to charge carrying currents, charge carrying wires. There's one more that I should point out, and that's this. If I've got a wire that's carrying a current this way, and I'm looking at a location here, so maybe it carries current this way and then it turns and goes this way, I would say here is contributor number 1, contributor number 2. Contributor number 1 wants to spear right into the point that I'm looking at. So the B field due to 1 is going to be 0. If it's going to spear right in, I get no magnetic field contribution from that. The B field due to 2, this looks like a semi-infinite wire. So the B field due to 2 is going to be a half of a mu naught I over 2 pi r to where this distance is r2. I'm going to do a separate video that works through a couple examples, but for right now, that's all I need.